Conductors and insulators. Once you've charged it up, where does the charge go? Does it stay put, or does it run around all over the place? A conductor is a material whose electrons are free to move. If you've heard of the electron sea or the electron gas in chemistry, this is it. The electrons can go anywhere they please. Consequently, they will. Charge one part of an object, you charge the whole thing. The charge quickly spreads across the entire object, and that means, from a macroscopic, hold-it-in-your-hand physics perspective, the entire surface of the object is basically charge. You're not going to notice any delay between charging the top and charge appearing on the bottom. Insulators are materials whose electrons are shackled. I wouldn't say they're not free to move. That would be a violation of quantum mechanics and Heisenberg uncertainty. Electrons are always moving, but they move within their own atoms and their own molecules. They don't go joyriding through other people's molecules. Now, which materials are which? To determine if it's a conductor, ask yourself two questions. Number one, is it metal? If the answer is yes, then it's a conductor. Copper is a very good conductor. That's why it's used in electrical wires. Silver is a better conductor. That's why high-grade electrical wires are silver. Gold is the best conductor we have. That's why fancy electronics are so expensive. Their circuit boards are plated with gold. On the flip side, this is why electronics recycling isn't just good for the environment, because these heavy metals leach toxic chemicals into our water supply if we try to dump them and landfill them. But hey, if you can reclaim some of that gold from off those circuit boards you're recycling, you could actually break a profit on your business. If the answer is no, it's not metal, start with the obvious, it's a liquid or a gas. Move on to your next question. Is it ionized? Solid, liquid, or gas? If it's ionized, it's a conductor. One way is to look for the word ionized in its name. If it's ionized water or ionized gas, that would be a conductor. Acids are also ionized. Things like vinegar, things with salts dissolved in them, have those nice Na and Cl ions you learned about in chemistry. If it's not metal and it's not ionized, it's an insulator. Common insulators include rubber, plastic, ooh, look, electrical insulation, wood, deionized liquids, deionized gases, cloth and wood are insulators, and anything else that you typically use as insulation for heat. Consider it. Heat is average molecular kinetic energy, and if your electrons are running around all over the place, zapping things, they're going to have a lot of kinetic energy. That means if you're a good insulator for heat, you'll also be an insulator for electricity. Also, if you're a good conductor of heat, you'll also be a good conductor of electricity. Let's see, what else? Liquids, gases, deionized liquids, deionized gases are not good conductors. They don't have the ions. Let's consider an example. Let's talk about water. Is water a conductor or an insulator? Pause, think about it, press play. Check. Is it metal? Is it ionized? Distilled, deionized, chemistry, pure H2O with nothing in it, water, is not a good conductor. It's not ionized. All those warnings about your toaster and your hairdryer and keep them away from water and don't let any of these electrical devices touch water, they're talking about tap water. It's not the water that's the biggest problem. It's the ions in the water. The fluorine that keeps your teeth healthy, the chlorine that kills the germs, all those wonderful minerals, which is why we call it mineral water, they're all ions, and that's what's responsible for a lot of the electrical conductivity. Deionized water is a very poor conductor. What about air? Insulator or conductor? Well, if it's not metal, it's not ionized, it's an insulator. What determines electron mobility? Why are some electrons in some materials free to move and others not? The ion question is very straightforward to answer. elements, atoms, and molecules want to be balanced. They want to have the same number of protons and electrons. A negative ion has too many electrons. This throws its system off balance. It is unhappy and wishes to get rid of them and to restore its happy electrical neutral state of equilibrium. Positive ions have too few electrons. Electrons are missing, they are mad about it, and they wish to snatch and steal electrons from other atoms in order to restore their own equilibrium. Atoms everywhere say, negative charge, I don't want it, you take it. Oh, I don't want it, you take it. I don't want it, toss it over to her. I don't want it, pass it to him. And thus there's a lot of electron mobility. Positive ions say, give me those electrons. I want them. No, I want them. No, I want them. The electrons get snatched and shanghaied and carried off from place to place, and there's a lot of electron mobility. What about metals? What's the secret for metals? The secret to metals has to do with the shape of their orbitals. When we start on the top left of the periodic table, The secret to metals has to do with the shape of their orbitals. When we start on the top left of the periodic table, we start filling s orbitals, 1s1, 1s2, 2s1, 2s2, and then we move into p's. S orbital is spherical, or a higher level s orbital is a set of concentric spheres. They're very easy to fit things into. A p orbital is shaped like a figure 8, one in the x, one in the y, and one in the z direction. All together, again, a very nice shape that's easy enough to draw. But a d orbital is something else entirely. If you've never drawn a d orbital before, let's just say there's a reason for that. The transition metals is where the first spot in the first d orbital opens up. An s orbital has very limited electron mobility. There's only room for 2 electrons in each orbital. There's really nowhere to go. It's not very interesting. Similarly, a p orbital has room for 1 electron in each lobe, like rooms of a hotel. There's nowhere to go, and it's not very interesting. A d orbital has so many separate extra dimensions. The electrons can go anywhere they want, as long as they're still in somebody's room, in somebody's orbital, some of the time. Where we have d orbitals, we have room to play. Where the d orbitals are full, of course, all the rooms are full, and electron mobility is restricted. But where the d orbitals are almost full, you've got enough interesting places to go to be worthwhile going, and it's not so crowded you're tripping over other electrons on your way, and we have the best conductors, copper, silver, and gold, with their d orbitals mostly full.